All right, in this podcast, we're going to talk about how to write the electron configuration for ions. All right, so basically, if you want to go ahead and write the original electron configuration and then look at your charge. If it's a positive charge, then you remove the valence electrons. So you need to know which electrons are valence. So what you want to look for is you want to look for the electrons that are in the highest shell. So see how right here there's a 3 there? That's the highest shell that you have. These are all lower than that. So that is actually the valence electron. So if it's a 1 plus, like right here, then we're just removing this 1 valence electron. If it said 2 plus, then we would have to go down another shell and start messing with the electrons in that shell. All right, now if it has a negative charge, you're going to add electrons. So here we have a 2 minus charge, so I'm going to add electrons to the valence shell. So here's the valence shell, the 2p. So there's 2 minus, which means I'm going to add 2 electrons, and the p can hold up to 6. So it's going to make it 2p6. So it actually makes it have a full octet. So everything is full. All right, now transition metals are a little harder. Transition metals are metals, obviously. Because they're metals, that means they're going to have a positive charge. They always lose electrons. But their valence electrons are not the very last one written like they were in the 2 previous examples. So let's take copper, for example. So here's the electron configuration for copper. You see that the last electrons that go in are the 3d9s, right? But if we're going to make it a 2 plus, that means we need to remove 2 electrons. Now, if you're looking for the very highest shell, which means the very highest ring, this is the valence shell, okay? So this is the outside ring. So because it's a 2 plus, that's what's getting eliminated, okay? So the last electrons in that are filled in a transition metal are not the valence electrons. So you got to be mindful of that. All right, now, if an atom or an ion has the same electron configuration, we consider them to be isoelectronic. So what that means is they all have the same number of electrons, same electron configuration, but they're not actually the same element because they have different numbers of protons, and then some of them will have charges. So for example, if we wrote out argon, argon is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so there's argon. All right, now potassium, if you were to look at the periodic table, it ends on 4s1. So 1 plus, we're going to remove that 4s, and it's going to be back down to 3p6. So just like argon. And then chlorine would be a 3p5, but because it has that 1 minus, we add the electron. So that'd make it a 3p6 as well. So if you notice, the trend for all atoms is for them to form ions that make them have the same electron configuration as a noble gas. And that's because noble gases have full octets, therefore they are highly stable.